course you can see. So what is the correct answer? Yes? Okay, so if we don't have intuition, we just use our methods, okay? So I got this way, okay? And I'm going to analyze the forces acting on it, okay? So I surround my object with an imaginary surface and say, where is this thing touching the environment, okay? And it's touching it here, one string and the other string. So this 1 point and this 1 point. Okay? And so, so it's tension 2 here and the tension 1. And these are all the contact forces. Is there any long range force? Yeah, the weight. Okay? So these are all the zoo of forces for this my problem. So now I am ready to draw the free body diagram of my object. My object is the point, the free body diagram, and I put all the forces there. Okay? And remember that with the free body diagram, all the forces go with the tail on your object, whether you are pushing or pulling, okay, it doesn't matter, okay? All the force, the tail of the force has to be on the object, okay? So you'll agree with me that this is the proper way of doing it. So this will be T2, this will be T1, this will be FG. Okay? Any objection to this? So what else could we guess here just from symmetry? What would be a good assumption we could make to make the problem? That the magnitude of the tensions are equal. Okay, we could actually prove that. Okay, but because we don't have much time. So we could say T1, magnitude of T1 is equal to the magnitude of T2. Not T1 and T2, of course, because they are opposite, so they're different. They are not different directions, but the magnitude. So we can call that just T. Okay. So let's suppose, let's call this angle theta here, and let's use Newton. Okay. So mass times acceleration in the y direction is equal to 0 because nothing is moving here. And this is equal to the sum of forces in the y direction. And what is that? That is the y component of T1, the y component of T2, and the y component of the weight. Okay? So this will be, because the magnitude is just T for both of them, okay? So this will be T cosine theta plus T cosine theta minus mg. That has to be equal to 0. Okay? If we have not assumed that the forces were the same, the magnitude were the same, we had to write an equation for the x direction. And then we had two equations, and we solve the two equations, we find that the two tensions are the same. Okay, but because we made this assumption, because we are smart, okay, we just simplify it. Okay? And so 2t cosine theta minus mg equals 0. So t is equal to mg over 2 cosine theta. So what is this telling me? So now we solved the problem, but we still need to figure out what it means. Okay. So is the tension always the same? No. Why? Because the angle is not the same for all of them. Okay? Now, when the angle is 0 is when this thing is, the strings are perfectly vertical. Okay? So that's when the cosine is 0. Cosine of 0 is 1. Okay? So as we start to open, okay, what happens with the cosine? The cosine gets smaller. Okay? It's the cosine, remember the cosine function, okay? That's this. Okay, this is 0, okay, this is 1, okay? So it starts, cosine of 0 is 1, and then it goes down. Okay? So we start to open up, okay, this thing is smaller, which means that the tension is bigger. Okay? So the tension, so the correct answer here would be that, that for block 1 is the magnitude of the tension the largest. Now, now that we can solve the problem mathematically, okay, so you can see what is going on here. So you have a weight down, okay, that you have to compensate for. Now you have a tension, okay, if you open up, the y component will get smaller. So, but the y components have to add up to the weight, because the sum of forces in the y direction has to be 0. So the y component of the two tensions have to add up to the weight. If you open this thing up, you're making the y component smaller. So you have to make the tension bigger to keep the same value for the y component, because you are being forced by the problem to do that. Otherwise, this thing will fall. So if you make it, in the extreme case, you make it perfectly horizontal, you can't do it. Okay? Because no matter how big, you never get any y component. Okay? So if it is an angle is infinitesimally small, you need a huge tension. That's why if you have a horizontal thing and you hang something from that, it will always bend. It is impossible, it will not bend. Okay? So you cannot have a horizontal string, hang something and leave it, and this thing remain horizontal. It will never happen. Okay? Because you need a huge force to do that. Okay. So we need to find the magnitude of friction on these 5 forces below. Okay. What happens with the first one? What is the friction force in the first case? Okay. So the friction force in the first case is 0. Okay, why is that 0? Because friction is a very lazy force. So if you only act, it is forced to do so. So if you don't push the box, the friction doesn't need to do anything. Okay, there will be no friction force. In fact, if there was a friction force, then this thing will start moving spontaneously. Okay, so it doesn't. Okay, so the first case, okay, y is 0. Now, so what happens after you start pushing? So now you get some friction force, and the object doesn't move. Okay? You increase your push, and the friction force increases. Of course, the friction force opposite to your push and equal so that they cancel out and the object doesn't move. But you can't do that forever. Okay? You get to a point where your push is so hard that what is called the static friction force can't compensate for that. Okay? And that's the highest possible friction force, and that appears in which case? In the second one, because it's on the verge of slipping. So that's the highest force you can apply. So the push is the highest push you can apply without this thing moving. So F2 will be largest. Okay? These are the first one, and the first two ones are the ones in which the box is not moving. So this is static friction. The other three, the other three, the box is moving. And so we have kinetic friction. And kinetic friction is a constant force. It's always the same. And it's given by your coefficient of friction times the normal force. Okay? Now, if you put here the push, and here you put friction, so you start from zero push, zero friction, and you go up to this point, on the verge of slipping, and this number, this here, this is the static friction times the normal force. And then if you increase your push even further, the object will move. And when it moves, it switches to the regime of kinetic friction. And kinetic friction, what you have is a sudden drop of the force, and then you have the same value. And this is equal to the kinetic friction, coefficient of friction times the normal force. Okay? So the five situations in the problem that you have is one is here, and the other three are here. Okay? And so this one is the largest when you're in the verge of slipping. Okay? This one is the smallest, and these three are the same. Okay? So that is the I did this right, it should be 1. F2 is greater than F3. Yeah, the last one. Okay, F2 greater than F3, equal to F4, equal to F5, and greater than F1. So the last one here is the correct solution. Okay, since we are into friction, let's look at another problem, okay, that some of you were talking about.